Last lecture was on T to Z mode in a rectangular waveguide, and this lecture is on TM to Z mode in a rectangular waveguide. This lecture I will not be using any animation at all. We are going to simply flip through the slides, and I will show you how to see the equations. Okay, it's a different experience. Trust me, you need to do this, and you need to go through these equations on a piece of paper. Please write them down. But the way I am going to be showing that is in a very different way. Now, I want to solve transverse magnetic to Z, TM to Z. TM to Z is characterized by Hz equal to 0. Yes, we know this. This is obtained by making A equal to AZ cap AZ and F equal to 0. Next step, you are going to write the electric and magnetic fields in terms of AZ. And AZ itself is written as a product of a function of X, a function of Y, and a function of Z. We know these equations. So what is the next step? Step is we are going to use variables, separation of variables method, and write down three differential equations, one in terms of X, one in Y, one in Z, where beta x square plus beta y square plus beta z square equal to beta square. No difference between the previous one, that is TE to Z, and this one, which is TM to Z. The next step is go to the boundary value problem, rectangular waveguide, and write down the solutions for fx, gy, hz. We choose a positive z traveling wave, therefore we choose hz as a3 to the power of minus j beta z, and write the equation for az in terms of beta x, beta y, beta z, c1, d1, c2, and d2. We have to evaluate all these constants. Good. What is the method we're going to do? We're going to apply the boundary condition. For that, we have to calculate Ex. This time the equation is in terms of Az rather than it was Fz in the previous case. So we know the equation for Az. Substitute in this, differentiate with respect to x and z. You get a result here and force the boundary condition at x equal to 0 and at y equal to, I'll pull out the laser pointer here, at y equal to 0 and y equal to b, because Ex goes to 0 at y equal to 0, y equal to b. When it goes to 0 at y equal to 0, we get C2 to be 0, and y equal to b, Ex becomes 0, implies sine beta y by beta y b equal to 0, or beta y equal to n pi by b. Do you see how quickly we are covering these slides? Trust me, it is not that fast. When you start writing it down, it will slow you down. Therefore, my request is stop this now. Give a pause. The next step, enforce the boundary condition at x equal to 0 and x equal to a. Which component will go to 0? Ey will go to 0. Evaluate Ey, write the equation for Ey and enforce the boundary condition at x equal to 0 and x equal to, and what you get is this result here. You have beta x is m pi by b and c1 goes to 0, and hence you have az given by bmn sine m pi by a times x sine n pi by b times y e to the power of minus j beta zz. See, the whole strategy here is it becomes very repetitive, very monotonous. That's what we want it to be. What we are trying to learn is a systematic procedure which you can simply apply to any given case. Suppose if I ask you to calculate T to X, can you visualize the process you're going to be following? Or Tm to X, can you visualize the process you're going to be following? Please, practice that part. That is what is very important. Now, these are the field equations. Once again, as I said earlier, you need to substitute Az into each of these equations and perform these derivatives and then ensure that these equations are correct. This is important that you write them down and do it once. Otherwise, you will not get the speed. In the exam, two things are important. One, knowing the method. Number two, having sufficient speed. And third, this is important, maintaining accuracy. So speed and accuracy, it is like, opposing things. Cutoff frequency, absolutely no difference between TE and the TM mode. Therefore, uh, if you were to say that TEMN and TMMN modes are degenerate modes, well, I'll give it to you, because both the cutoff frequencies are identical. They are two different modes. Therefore, they are degenerate always. Right. Now we have propagation constant, which is given by this result here, which is again very similar to what we saw in TE to Z mode. No difference at all. Phase velocity, once again, no difference. Same set of conclusions will apply. This is going fast, isn't it? I'm literally jumping slides. Well, there is nothing new in this. It's just set of equations. Lambda g, once again, no change. Okay, the wave impedance is something is little different compared to TE to Z mode. So we'll spend a moment to look at the wave impedance for TM to Z mode. Definition is still the same. It is Ex upon Hy, which is also minus Ey upon Hx, which is equal to now slightly different. Look at Ex. I'll pull out the laser pointer. Look at Ex and Hy. Take the ratio. Minus sign will cancel. Bmn will cancel. Beta z by omega mu epsilon upon 1 by mu. Mu will cancel. We are left with beta z by omega epsilon, and all these terms are exactly identical. They'll all cancel. So we have beta z upon omega epsilon, and beta z is known by these equations. That is same as TE to Z, and therefore wave impedance is eta times square root of 1 minus Fc by F whole square for F greater than Fc. For F greater than Fc, this quantity is less than 1, therefore this term is less than 1, therefore the impedance is less than eta. And as F goes to F is equal to Fc, the wave impedance becomes 0. And for F less than Fc, the wave impedance is purely capacitive. There is a negative sign that is coming here. That is because of the negative sign which is in beta z.